Hi, pre-calculus students. Are you ready for another lesson on logarithms? Super exciting. Okay, so today we are going to review the logarithm properties that we talked about last time, and we're going to talk about graphing. So graphing calculator or decimals for the graphing. Okay, so you should be on page 14. We're going to do the examples on page 14, and then we're also going to do the graphing examples on page 17. So that is the plan for today. Okay, at the top of your page, you have a summary of the properties that we talked about last time. So at least 3 of them. There are a couple of other ones we haven't talked about just yet. So you've got the product property, right? So that if you have the product of two things being multiplied, you can split it into a sum. If you have a quotient, you can split it into a difference. And then this one with the power, where I can take that power and drop it in front. Okay, this next one, the equality property, we're going to use next time when we talk about solving. Right? So if I have log base b of m equals log base b of n, so they're both log base b, then that means the m has to equal the n. And then the last one is called the change of base formula. Okay, so the graphing calculators we have now, we can put any base we want into them, but they didn't used to. They were always just either a common log, base 10, or natural log. So when I was in high school, all I had to work with were common log and natural log. So if I wanted to figure something out like the log base 2 of 10, I couldn't do that without a log chart. And that's what we had in the back of my pre-calc book. There was a chart, and it would have like the different, it wouldn't have different bases. It would have all the different log values. So we needed a way to figure out something like log base 2 of 10. So what we could do is sort of think of it like this. And if I rewrote it as 2 to the x power equals 10, if I put it in exponential form, then what we could do is use this idea of taking the log of both sides. And we're going to get more into this next time when we get more into solving equations, but this is where the change of base formula comes from. Okay, so if I were trying to solve that equation for x, I would put the x in front. And then to get the x, I would divide by 2, the log of 2. And so this log base 2 of 10, this is supposed to be a 2 over here, is equivalent to the log of 10 divided by the log of 2. And I can do the log base of whatever I want on both sides. Back in the day, we'd always do log base 10 or log base e, because our calculators, our scientific calculators, only had those options. So when you compare these two things together, and that's what this is saying over here, log base a of n, I could rethink of it as log base b of n divided by log base b of a. And again, the base can be anything you want. So usually we would just pick 10 or e, but you see how the n is on top, and then how this little a is the log on the bottom. Now this is a little different than these other ones where like it would condense to a single log. This is actually a log over a log. So we'll see some examples of that, but it's just a workaround for if you had a scientific calculator that you couldn't enter any base that you wanted. So we've been talking a little bit already about special logarithms. So common log is a log with a base of 10, right? So it just means the base is 10. So instead of writing log base 10 of something, it would just be log of x. So when there is no base written, like we've said a couple times before, it just automatically means the base is 10. Natural logs means you have a base of e, so that number 2.71828 with that 1828 repeating. So instead of writing log base e of x, kind of clunky, it's just written as ln of x or ln of x. I don't know, sometimes my L's start looking like 6s and then I connect them and I don't know. So natural log of x. So it's just some special notation. All right, so let's take a look at these examples here. And I believe you did things like this last year, so hopefully they seem a little bit familiar. So you're given that the log of 5, you're given that value. So this would be something like back in the day, I would have had to look in a log table to figure out that value. So if I want to know the log of 50,000, I want to think, is there a way that I could rewrite 50,000 using a product, a quotient, or a power to figure out the log of 50,000. So I know the log of 5, and remember, you always know the log of powers of 10. Like you know the log of 10 is 1, or the log of 100 is 2, or the log of 1,000 is 3, or the log of 10,000 is 4. So you know all of those. So if you got 5s and then powers of 10, could you get to 50,000? And then same thing with this other one. If you had 5s and powers of 10, could you get to this 5 1,000? So take a minute and think, is there a way that you could rewrite these numbers using 5s and powers of 10? Okay, so what I might do is I might rethink of this as 5 times 10,000. Right, 5 times 10,000 is 50,000. And then I can use my multiplication, my product property, that I can rewrite that as a log of 5 plus the log of 10,000. Okay, then I know what the log of 5 is. It's that 0.6990 plus, this means 10 to what power is 10,000? So that would be 4. And then I can add that. So 4.6990. Excuse me. All right, this one, we had something like this come up before when we were evaluating logs, and we talked about if it's 5 1,000ths, you might want to rewrite it as a fraction instead of leaving it as a decimal. And so this is a log of 5 over 1,000. I see that's a quotient, which means I could rewrite it as a difference. Okay, and that log of 5 is 0.06990, and minus the log of 1,000, I would think 10 to what power is 1,000, which would be 3. And then we would do that subtraction. All right, so then we would have 0.6990 minus 3, and we would get negative 2.301. Okay, so we want to do the same thing with this next example. So we know what the log of 2 is, we know what the log of 3 is, we know what the log of 7 is, and then we can easily figure out the logs of anything base 10, right? So like the log of 20,000, similar to the log of 50,000. So first try these on your own, see what you come up with. Okay, if I were giving this to you in class, you would only have a basic calculator. So you should not be just plunking these into your calculator. Okay, so this would be 2 times 10,000. So I could write that as the log of 2 plus the log of 10,000. So then that would be 0.301 plus, again, that would be 4. So 4.3010. Okay, so now log of 14. How can I use 2s, 3s, 7s, a combination of those, and multiplying or powering or dividing to get to 14? So you might think, oh, I could do 2 times 7. So this is the same as the log of 2 times 7, which would then be the log of 2 plus the log of 7. So then I could add those values and see what we get. So we get 1.1461. Okay, now the last one, log of 18. So you might be looking at that and saying, well, 2 times 3 is an 18. I can't divide anything to get to 18. And this came up a little bit in our last lesson where we could think of using like powers. So you might say, oh, I see a 3 up there. 3 goes into 18. So maybe you're like, oh, I could rewrite this as, 3 times 6. But you're like, oh, there's no 6 up there. Is there a way that I could rewrite the 6 using 2s or 3s or 7s? You might say, oh, I could rewrite 6 as 3 times 2. Or maybe you were thinking of 9 times 2. And there's a 2 that we have information about, but then what about the 9? You could rethink of the 9 as 3 times 3 times 2. See how they're the same. It doesn't matter. So we talked about this a little bit last time, that you can now split this into the log of 3 plus the log of 3 plus the log of 2. If you wanted to be really fancy, I guess you could have done like log of 3 squared times 2, and then the log of 3 squared plus the log of 2, and then thought of it as doing 2 times the log of 3 plus the log of 2. Right? But the 2 times the log of 3 means the same thing as that. So the log of 3 was at 0.4471, so I do 2 times that 0.4771 and then add the log of 2, that 0.3010, and I'm getting 1.2552. I'm sure somebody is going to find I made some mistake when I put it in my calculator. It's just inevitable. Okay, so then this last one, example 5, we want to use that change of base formula. Okay, he hasn't given me any other information. So we're using that idea. If I have the log base b of, or they used up there, I'll do the same thing. The log base a of n, they rethought of as the log base b of n over the log base b of a. For my base, I would just pick 10, right? So they're just logs, okay? In this case, in the spot of my n is the 1043. The physically bigger number is what goes on top. And then the 9 is in the spot of the a, that will go on the bottom. So I would just do the log of 1043 divided by the log of 9. And I would just type that into my calculator. So yeah, you can kind of see it, not too bad, right? Okay, so log is over the 10 to the x key. So here is the 10 to the x key. We want to hit control. So control 10 to the x. And then I just want to do, I obviously know I could type in the 9 and the 10, 143, and I could get my answer. But we're trying to use this change of base. So if you leave the base blank, it will default to 10. So I'm going to do the log of 1043. You have to bump out before you divide by the log of 9. Hit control enter if your calculator's not in that mode already so that you get a decimal and not some funky answer. So 3.163. All right, and then that would be the same thing for this one. I could do the log of the physically bigger numbers, the log of 5, or 15 rather, divided by the log of 3. So log of 15 divided by the log of 3. Right, and then you could just type it in. Okay, when you're doing the practice, please try to use the rules. I know like all of this stuff, you could just type in your calculator. Please try not to. Okay, so that's just a quick review of the properties. Oh, that's fun for next time. All right, last thing we're going to talk about today is the graphing. Okay, and we're going to use the calculators to graph, so it's not going to be too bad. Okay, before we had the Inspires, when we had to graph, it was a huge, 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 huge pain. So just be grateful that we have them. Or Desmos, you can use Desmos also. Okay, so here's our exponential growth and our exponential decay. Remember how we had said before that exponentials and logarithmics, they're defined to be inverses of each other. And when we talked about inverses back in chapter 3, we talked about how inverses are a reflection of each other over the line y equals x. So if I were to take my pink graphs, reflect over that dashed line y equals x, this is my logarithmic graph. Okay, so it has a vertical asymptote instead of a horizontal asymptote, but it's just a reflection of that exponential function. So you just want to be careful when you're graphing it that it's leveling off vertically instead of horizontally. There you go. Okay, so for example 5, we want to first graph the log base 3 of x. So I'll show it to you here and I'll show it to you in Desmos, and you can use either. All right, so if you're using the Inspire, I am just going to make a new graphing document. Okay. And I can just hit control on that 10 to the x and put my base of 3 in and then type in my x. Okay, it really was. You guys don't even know. It was such a pain to teach this before. But having these calculators makes a big difference. Okay, so then you can see there's my inverse of the exponential, my 3 to the x. There's my log graph. And I would just hit Control T and look at the table and plot some points and arrow up. And you see what happens when you get into that negative region. You can't take the log of a negative number. We haven't really talked about that yet. But let's think about this. If I did the log base 3 of, let's say, negative 3, and I was thinking 3 to what power equals negative 3? there is nothing that would work, right? If you have a negative power, it makes it a fraction. It doesn't make it a negative number. So you can't take the logs of negative numbers. That's why it's leveling off there at the y-axis. So then when you look at the table, it might be a little deceiving if I just go by ones, like, okay, I've got the 0.10. I'm going to look for a couple of friendly numbers. Here's 3, 1. I think the next one's going to be 9, 2, right? Which would be kind of over here. So if you just looked at the table, you might think, oh, it's just kind of like almost looks like a square root graph. Okay, but when you look at the picture, you see it clearly is going down, because you could have done something like the log base 3 of like 1/2, right? And then you're going to get like smaller numbers. So this does go down here. Okay. So it does approach. Don't just count on the calculator. Okay. The table in the calculator. You know that it continues going down. Right. And then if you look at this one, you should be thinking back to chapter 3. Oh, it's a +3. It's a +1. This +3 is going to tell me that it goes to the left 3. And this tells me that the whole thing is shifted up 1. So now I have a vertical asymptote over here, which you'll see when you graph it. All right, let's get out of here for a second and go into Desmos and graph this second one. Okay, so y equals, oh, I want this to go away. Hide. Oh, how do I get my thing? This happened before, right? I don't do it enough. You would think I'd have this down by now. I don't. All right, miscellaneous. Log of x plus 3. How do I get the base? No. Guys. Oh, I meant to practice this before I started the video and I totally forgot. That's not right. I need a base of 2. I hate it when I do this. I'm sorry. All right, let's go to the calculator, and then I'll figure this out, and then I'll let you know what I did wrong, because there's always something, right? And I just, like I said, I love you guys, but I don't have time to make another video. I just don't. Though what we could do in Desmos is use the change of base formula. It's just kind of a pain. Ugh. Kind of a pain to enter it that way. Okay, so log base 2 of x plus 3 and then plus 1. So they're going to look similar, like you're probably thinking that's what it looked like, but it is a little bit different with that base. Okay, so I'm going to hit Control T and look at my table. You'll see it's not going to give me the undefined until I get to that -3, which is where I have that vertical asymptote. Right? And then I can plot -2, 1, -1, 2, 1, 3, and so on. Let's see. So right now I'm thinking if I had to enter this into Desmos, right, because I just don't have an Inspire at home, which a lot of you probably don't. If I rewrote this with a change of base formula, it would be the log of x plus 3 divided by the log of 2 and then plus 1. So we could enter it in like that. Okay, so let me just show you so that you could do this if you had to. Okay, so the log of x plus 3 and then divided by the log of 2. And you can just type, I just typed log because I'm on a laptop. And then plus 1. Okay, and so there you see we're getting the same points. So you would use that change of base formula that we talked about. See, that's another reason we want to have it. I feel like there's got to be a way in here. I'll figure it out. All right, so that is where we're going to stop for today. And then we'll get into solving equations next week. Take care, everybody. Now let's see if I can get out of here, right? Oh, goodness.